let's think a little bit about how to make some of these reagents of organolithium, and then hopefully the magnesium on the Grignard reagent, so that then we can we're starting to think about the reactions of these compounds. And we've already seen the mechanism. We're just going to add some more detail to it. So to show a little bit of how these compounds are made, I don't want us to memorize these, but just to be aware of how they're made. So organolithium compound, we'll use some generic alkyl bromide. The way this is typically made is to take lithium, the actual metal. So these are very reactive species. We need a solvent that's not going to react. So in the first semester, you would have seen that diethyl ether here. Or just simply known as ether a lot of times, is the solvent. This is done at a slightly lower temperature, minus 10 degrees Celsius, and this is used to make this lithium species. And then to balance this, it's going to be plus lithium bromide. Now, there are lots of other organolithium species that can be made, but let's just stick with this one. So now let's use this organometallic reagent that we've just made and use this in a reaction, so that with an organolithium compound. Let's use that same, I think I can draw that a little bit better. Let's see. Slightly better. Let's react this with acetone. So we have a ketone. There's our carbonyl group. And this is going to give us our most basic, this doesn't always mean easy, but basic type of a reaction that we're going to see with these organometallic reagents. So we know that we have, again, this dipole. Oxygen is more electronegative than the carbon. We could draw the resonance structure. So we know that this carbon here, let's use green instead of the part, this is going to be our electrophile, or that carbon is electrophilic. And now what we've just seen is that for this lithium-containing species, this is really like, we'll keep it in bond line structure, so 4 carbons, it's really like there's a negative charge in that carbon, and the lithium has a positive charge. It's our imaginary species. So now this is going to be a strong nucleophile. We'll just put strong nuke there for short. So in terms of a mechanism, just like before when thinking about nucleophiles and electrophiles, we'll use, let's just use the bottom one since, we'll use the top one since it's correct. Let's have this attack here. Move these electrons up onto this oxygen. Now, just like what we saw before, rather than using a generic NUC for the nucleophile, now we actually have this organolithium species. So we're going to have a tetrahedral intermediate. We've moved electrons up onto this oxygen. So we're going to have a negative formal charge. And here's the key thing, is we formed a new carbon-carbon bond. So we have our carbon of the carbonyl group, the ketone, just shown here. And we've added 1, 2, 3, 4 carbons on the left. 1, 2, 3, 4 carbons. Now, a little bit more detail is if we wanted to balance formal charges, our lithium ion is going to be hanging out and coordinating with that oxygen. And now we need to look to see, do we have a leaving group that we can use? And so we have carbon, carbon, and if this were to leave, it'd go back to what we started with. Carbon is going to be a bad leaving group. So what we'll do in reality is we let the reaction go, and then in the end, we might just add in a little bit of water carefully that's slightly acidic. So I'll put a generic acid there, and we're going to simply protonate this. Alcohol, and then 4 carbons. And we'll have our lithium in there as well someplace. So what we're seeing here overall is we're taking a ketone. Let's put the names in here as well. Do it in green. In this case, we started with a ketone, reacted it with our organolithium reagent, and in the end, we generated an alcohol. And on top of that, we formed a carbon-carbon bond, a carbon-carbon bond, CC bond. So this is a very powerful reaction because we can take all sorts of different carbon nucleophiles, form a new carbon-carbon bond, go from a ketone or other functional groups, as we'll see, to this tetrahedral intermediate, and then eventually to our alcohol in the end. Then there's chemistry that could be done with that alcohol if we actually wanted to do that. Now, one last component of this reaction is we've gone from something that's sp2 hybridized, that ketone, to this sp3 hybridized carbon on the right. And so everyone's favorite topic of stereochemistry is still part of this and may come into play. And we'll see in a lot of reactions, if you can form stereoisomers, you will. We'll ignore it sometimes, even though you may actually form them. But this one I chose intentionally, just finding I'm a different color, is that if you could form stereoisomers, you would. But remember how to define if you have a chiral carbon, is it's a carbon that contains 4 different groups on it. This one contains alcohol, there's a butyl chain, those are 2 groups, but then a methyl and a methyl, so 2 groups that are the same. So this one is not chiral. That was done to simplify. Okay. Everyone excited about that? Our first organometallic reaction. Again, I'm just assuming everyone's shaking their head yes. Yep, okay. Hopefully not shaking your head to try to stay awake, but that's also a possibility. So then we have a few more minutes. All right, yes, exciting with an exclamation point. That's fantastic. Now what we're going to see is another organometallic reaction. Instead of using the organolithium reagent, we're going to use a magnesium-based reagent. And if you're looking at this as we're going through some of these things and saying, well, the mechanism looks the same over and over and over again, it's likely because it is, which is actually a good thing in terms of organizing this. And these magnesium-based reagents look slightly different than the lithium ones, but the mechanism is essentially the same. And this is such an important reaction that was discovered by a person named Victor Grignard. So he was French, so it's not I don't know how to say it improperly. It's not Grignard, but Grignard reaction, or at least something of that sort. And Grignard reagents, you'll hear that name a lot. Oh, let's react with a Grignard reagent and use a Grignard reagent. What does that mean? The Grignard reagent is generically this RMgX in the middle. And what it is R is some alkyl group. Could be a methyl group, could be 1,000 carbons, but it's some alkyl group. Mg is magnesium, and then X is a halogen. Typically iodo, bromo, or chloro is a halogen. And I'll generally just use bromine because it's a little easier to see compared to iodide. Looks like a hydrogen on its side, and chlorine can look like a carbon with my bad handwriting. So that's why I'm using bromo as the X, but it doesn't have to be bromine. So let's think about how to actually make one of these Grignard reagents, because we're going to end up seeing them so often. And we'll see that there's a couple of different types of Grignard reagents. So we can have, first of all, just a generic RX species that we might take. And then we react this with magnesium metal in the presence of ether. Let's put it underneath. And what you'll end up forming is something that's shown as RMgX. This looks like magic, but we'll cover it in a second. So we could take something like we did with the lithium species, react this plus magnesium, presence of ether, and we're going to end up with the magnesium kind of squeezes in there. It looks like MgBr. So this would be an alkyl Grignard reagent, AlKyl. You can also do this with aryl groups. It's part of the generality of this reaction. So we could take benzene with X presence of magnesium now. And we'll have MgX. So this is a little redundant, but let's now do the same. Oops. Try that again. Benzene. It's like bromobenzene plus magnesium. And we're going to have our Grignard reagent. So I hope you have the chance to do this in the lab and you're actually able to see each other in person and not through Zoom. It's a pretty exciting reaction to make. If you're looking for something to do, maybe you've already done this already, but just look on YouTube for like a Grignard reaction or making a Grignard reagent, and you'll see it's pretty exciting, but much more fun in person. You take magnesium metal, a ribbon, you scrape off all the oxidized surface, and then you mix it in with ether and your alkyl halide, and eventually you'll start to see, it's very sensitive to water, eventually you'll start to see the metal dissolve, and it goes into this kind of milky white solution to form the Grignard reagent. So it's pretty exciting, at least I think so. So then, just to kind of look real quickly as to how this might work, let's say, put another line across here, is we're going to be most interested with these species on the right, with what's known as the Grignard reagent. So this aryl magnesium bromide or this butyl magnesium bromide, those are known as the Grignard reagents. And it looks weird that it looks like the magnesium, as I mentioned, just kind of squeezed in there. The mechanism is likely quite complex, and this may not be entirely correct. But one idea as to how this actually works is let's take this alkyl bromide, and then let's react this with magnesium. And probably the simplest idea is it's a radical reaction. And I use this just to bring back the radicals. And I don't want us to memorize this, just to give us a sense of what might happen, is that we could imagine one of these electrons, using a single fishhook arrows, forming a bond with a bromine, and then the other electron in that carbon-bromine bond going onto the carbon. Seems weird because it's a primary radical, which we know is unfavorable. So we have our primary radical, plus now Mg, I'll put the bromine on this side with another radical here. And so now we could have a second step where we actually have these two radicals come together. Still have our 4 carbons, MgBr. Okay. And in this reaction, the ether is actually thought to help stabilize the Grignard species. So it's a Grignard reagent, I should say. Stabilized by ether. So this could be coordinated. So those little dots will mean to ether molecules. So some details into the reaction. All right, so those are our Grignard reagents. And this is going to be very important now because we can react these with a variety of different species. So I'll scroll up if that's okay for everyone. All right, so